So far we spoke of the linking mechanism. That is how the linker works internally, how it fixes up symbols and addresses and so on. Now we'll discuss about the linker control scripts. That is, we had just talked about the linker arranging the code based on the memory map of the STM32F411XE or XC, but even the linker needs the information about the memory layout and information about what we need to arrange where. For example, where the text section will go, where the data section will go, where the BSS section goes, where the stack goes, so on and so forth. So the linker needs to have a script that is fed into the linker during the linking process, which instructs the linker how to organize the output. So traditionally, linkers offered limited control over the arrangement of output data, traditionally. But as linkers started to target environments with complex memory organizations such as embedded microprocessors, like the one we are seeing here, where you have your flash in some location, the RAM is in some other location, and so on. It became necessary to provide finer grained control over the arrangement of both of data and the target address space in the output file. We will now focus on the GNU linker script language. This is called the GNU linker script language, and it controls the linker's output. So in our case, when we are programming on the STM32F4, okay, the ROM starts at address 0x08000000 and has length of 512 KB, and the RAM starts at an address of 0x20000000 and has a size of 128 KB. And this is a complex address mapping that the linker needs to be informed of. It is not a straightforward address mapping. And of course, the linker script is written in the linker command language. Linkers always use a default script which can be overridden by a custom script with the -t command, which you saw when we were running the linker command. We were giving the -t command. And for embedded systems like the one we are dealing with, a -t command always has to be a part of the command, because we will be supplying it with an external linker script with a .ld extension. Now, this is the example linker control script that we will see, and this is the script that has been driving our outputs so far. Please have a look at the GNU linker documentation, because the information that I'm going to provide you here is good enough for our course, but there is a lot more to linkers, and covering everything is not possible here because it's quite vast. So please have a look at the linker script. So especially chapter 3 of the GNU linker document, and there is a lot of information that you can find. Most of what I'm going to show you is derived from this document, and this definitely has a lot of good information that you can ingest. Right. So this is the document which is called the GNU linker. Download the latest version and please have it handy when you are working on the linker. Basic linker concepts will be covered in the course, but this document contains a lot of relevant information, and we will be going back and forth between this document and the slides. So let us have a look at the slide first, and then as required we will go back to the document. Now, writing a linker script file can be done in various ways. So this is one way that is conventionally followed, but then you might encounter some linker script which might look very different from what we have here. So we will cover this script first, and then maybe we will have some discussions as side notes as to what the variations can be. So the linker script contains commands like memory and sections. So sections is a command that is a must. Sections has to be there for a linker to work. Memory command may or may not be there, but in our case, the memory command is necessary because the kind of memory map that we have for our microcontroller can only be addressed using such a command, that is the memory command. Now, the memory command has again names like flash and SRAM. Now, these are names of memory regions. Now, these memory region names can be again different. So, it need not be flash, it need not be SRAM, but it should have a meaningful name. So, it is named as flash and SRAM. So, this within the memory command will be a description of the memory layout. So, we'll have so in our case we have a flash and SRAM. There could be memory where you have SRAM in different locations. You could have flash, multiple flash memory in different locations, so on and so forth. So you will have to have that many entries to describe the memory. For example, flash 1, flash 2, SRAM 1, SRAM 2, ROM 1, ROM 2, and whatever. Any name that makes sense. After that, within brackets, you have to put the attributes of the memory. For example, flash is RX, R for read only and X for executable. The SRAM is read, write and executable. And it talks about the origin also. So the keyword origin means where the memory starts from, here, and the length. So this is 512 KB and this is the origin of the RAM, and the RAM as we saw is 128 KB. Okay, so that is what is recorded here. So that is what is mentioned here for use later. So this is one part of the linker script file. Now comes the sections command. Now sections command is extremely important. This is where the actual actual work happens. This is the instruction for the linker to organize memory, and it is not difficult, but it needs some explanation. So dot text is the name of the section, that is the output section. So we spoke of dot text section. Now the dot text section is the output text section. That is, these are the input sections that should be going and sitting into the output object file dot text section. So this is the output dot text section, and these are the input sections. So these are the input section names and these are the input sections. So we'll go through the complete section command line by line. So the first line says underscore text is equal to dot. Now underscore text is it's called a linker symbol. Okay, so underscore text is a linker symbol, and this is something that we will need in the startup file. Okay, so underscore text is it's a linker. It's like a linker variable, but this variable only holds an address. So it is somewhat like a pointer variable. Okay, so all variables which are declared in the linker are like pointer variables, and this dot is it's a location counter. So this gives the virtual memory address. So right now dot text has the address of the current location counter. Now we do not know what the location counter is currently. We have not come up to that. Okay. Now, then we have star and then .isr vector. Okay. And we saw this section in the output file, if you remember. Output file and one of the input files, we saw this section. Now, now let us talk about the syntax of these sections, okay, of these lines. Now, .isr vector, as you know, is a section name for from a particular input file that we have created, and there's a star in front of that. Now, a star wildcard, so these are wildcards basically. So there are different kinds of wildcards that you can have. Something like a regular expression, and the linker document is going to give you complete information about the different kinds of wildcards that you can implement. In our case, we are using the star wildcard here. So if you look at it separately, okay, if you look at this separately, this means this could also have been written like this: star isr underscore vector, and then the particular object file that you want to extract this section from. So for example, it could be startup gcc.o. okay, so this could be a command which will tell the linker to extract this section from this particular file and move it to the output.text section. And if you remember, we saw the map file and we rearranged the files, and accordingly we saw that the arrangement of the .map, the memory layout changed. All of that is happening here. And I also mentioned something very specific, saying that no matter what the order of the files are, if you see, the ISR vector section is always on top because we made it to be on top. So that this is the reason why no matter what the order of the files are, we are always seeing the ISR vector section on the top, because the ISR vector section is something that we created, and it contains only the exception vectors. Okay. Now instead of startup GCC, the star means, so remember we had put in 3 file names, right? Build example main.c, core initialization xxx.c, and then startup gcc.c, and we also moved the order of these files around. This star means when you are feeding those files into the linker, that through the -t linker command, this star means all files. Okay, this star means all files. So in this case, only one file has the .isr vector section. Okay, but if you go to the next line, here star means all files which has the input.text section. Now .text section or code is present in all the files that are input, right? So what this command does is, whatever .text section you have for these input files are all combined together into one section and move to the .text section. That is what it does. That is the output.text section. This could have a file name, and star means any file name that comes in, just take that and add it to the next part of the .text section. Then you have RO data, that is read-only data. That is a constant data, whatever you have comes in here. So in the sense that this is how we have organized it. I mean, you could have RO data somewhere else, but then this is the convention. RO data could have been just after the ISR vector section also. You could move RO data here. It will organize the memory map accordingly, and when you open the .map file, you will see that the RO data has changed its position and it's gone somewhere else. Then again another variable, linker variable with a dot. This means now as it keeps allocating this memory addresses here, okay, linker is also doing all your relocation and symbol relocation and address fixing and all that. Okay, so all of this is anyway going on here. and then you have a dot here with a different variable name. Now what does this dot contain? It has filled up this region, so it has advanced by this many address locations, so it is in arrow data. So eText actually contains the next location, so it contains the next address location. Okay, whatever is the next address location. So it could be an aligned address location, it could be an unaligned address location, it could be anything. Okay, then this one is very important. So we do a greater than sign and flash. Now what does this say? Now greater than sign always stands for virtual memory address. Okay, so whatever we spoke of, wherever it was putting the information, or wherever it was putting the it was organizing the output input sections and moving them into the output sections, is in the flash. And flash, we know, starts from the memory location this, with a 512 KB length. So dot text equal to dot, when we put here, it actually refers to this greater than flash, and it starts counting from this memory location. That is the VMA starts counting from this memory location. Okay, so it starts counting from this memory location and it fills up the memory, and then when it comes here, say if this starts from 0 and it has occupied say 10 bytes here, this is going to be the location for the 11th byte. Okay, so this is pointing to the next memory location. So this completes the dot text section. So what do we see here? We saw that in a diagram on the slide also. That is, all the dot text sections from different files are combined into one dot text section of the output file, but not just only because it is a dot text section, but a lot of things go in there. The ISR vector is going in the dot text, and we are also putting in the RO data section in the dot text section. So this also goes in that section. We could actually probably have a different section defined for RO data. We could do all that, but in this case we have a RO data section going in here. Okay, then comes the data section. Now this data section is for initialized data. Now here is something that it's common sense, but it is actually missed out by almost all of us. Now if you are declaring a variable, say you are declaring a variable outside main. So this is, say, int a equal to 30. It's a global variable outside main. Okay. Now global variable outside main will also have its value being changed during the execution of the function. That's what we expect. Now you could just declare a global variable and not use it. That's a different issue. But generally common sense says that when you declare a global variable, it is going to be used. Now, but it has an initial value as well. Now when you are flashing the binary image onto the processor or onto the controller, this value has to be there somewhere. Though this value, since it keeps changing, eventually has to go and sit on the RAM area. But when the processor is switched off, you don't have an NVRAM or something here, right? That is done where it will hold the value. So in such cases, these values have to be first written into just after the flash memory. So we had written ISR vector, text, RO data, all of that is written in the flash area, but even the initialized data is written in the flash area. Okay, just after this. but this is a read only. We cannot use the data here, but it is just written here so that the data is available to the program when the processor starts up. But this data then for that purpose has to be moved to the RAM area, which we'll see in the upcoming slides. So it has to be moved to the RAM area now. Okay, so if it has to be moved to the RAM area, we will have to do something in the startup script. We have to copy this section into the RAM area. So what we do here is we declare the dot data area and do at. Now at is to set the LMA, that is where the code sits in the flash. Okay, you can take it that way, where the code sits in the flash when the processor is powered down. This is so when you do at, okay, and as you can see, what we are doing at is at address dot text. So we are using this variable at address dot text. Okay, no, and so we are we are not using this variable, we are using this section name. So it is at address dot text plus size of dot text. So this value is actually etext. Okay, but we are doing it in a different way. So this value is the value that comes just after this memory region, and we are setting the LMA here. So in the this data section is going to go and sit into the flash to begin with. Okay, so this is what it does. So of course this is the starting address, say whatever 8 with 6 zeros, and then plus this is 8 with 6 zeros plus the size of this section. Okay, so this size of this section, which is the address of the next free memory location address. Now sometime it is aligned by 4 bytes also, but will not do it, but it is also considered a good practice to do an alignment of 4 bytes before this section starts. Anyway, 4 bytes or 8 bytes or whatever alignment you want to do, double word or single word alignment. Now coming here, you have the underscore data. So this is another variable, underscore data. Now there is a subtle difference here. Okay, now the data, this points to the VMA now, and the VMA has changed because of the greater than SRAM. Okay, so this actually goes into the SRAM, but the whatever you see here puts the data. So let's be very clear about this. It puts the data with the boot image. So the boot image has the text section and the data is just coming just after this, as we saw here. But this section is not going to be used after copying this section over to the RAM. Once it is copied over to the RAM, then that memory location that this data is copied to is used for processing. After that, this section is useless. It is never used. So there may be some you can say that there is a bit of wastage of space, but then this is necessary. Otherwise, we will not get that information of the initialized variables, global variables into the program. So now it goes here, and this one dictates the VMA, that is a virtual, we call it a virtual memory address, but this is the actual execution address of the particular section. Okay, now similarly we have star.data. So all the files that you are feeding into this linker, all the .data sections will go and sit in the .data section here. Okay, now this .data section, that is the VMA, even though you see the VMA, okay, this will not be in the flash, it is going to be in the RAM. So your output output image that you have, binary image, is not going to have the data in the RAM actually. So this part is used by the linker to do the symbol fix-ups, right? That is, any variable, when it is accessing, say, a global variable from the code, the address of access is going to be the RAM memory. That is the memory location that is starting from here. That includes your stack and all that. We'll come to that later. So the logic points to this location, but the code is in the flash with the bootloader. So that is the reason for at and greater than SRAM. So this at could also come here. So you will see some convention where you have at sitting here also. Okay, coming to the next section, that is the .bss section. Now here you have the initialized. This section stands for the initialized data that we have declared in the program. That is the global initialized data. This section is for, in our case, this section is for the stack as well as the uninitialized data. Okay, so both of this go into the BSS section. So again, the BSS section, the VMA of the BSS section comes in here, and the VMA is actually the VMA here plus 1. Okay, but the LMA is the whatever. So suppose you have some LMA here, say which is say 10, but the VMA say is 50, because it changed here, right? So it is maintaining both the LMA and VMA. In the next segment, within here, the VMA is going to be say 51, and the LMA, so okay, so say the VMA is 50 and the size of this is say 20. Okay, size of this section is say 20, suppose. So naturally, what is your LMA and VMA going to be when it comes to this section? The section, it is going to be 10 plus 20, LMA becomes 30, and the VMA becomes 70, 50 plus 20. So that is what is being followed until and unless, provided you have not again declared a separate VMA for this section. That is, you have given an at again. If the at is not given, if the LMA and VMA has separated here in any section, that separation is, the linker respects that separation and maintains that separation in working the LMA and VMA up for the next sections. And again, these are two variables, that is which we will be using in our startup script. And as we saw, these variables are actually this is declared as an external variable in the startup script, and when we are using the variables, these values are actually filled up by the linker in those places. Okay. Though these are not variables that has been declared in code, but the linker fills up the values of these variables in the startup scripts. And greater than SRAM, of course, means we are putting this in the SRAM region. So if you are putting this in the SRAM region, it follows the VMA here from here to here. Okay, and this is the definition of whatever we had been talking about. That's the definition of sections. And the section says that it tells a linker how to map input sections to output sections. So this is the output section, these are input sections as we talked about, and how to place the output sections in memory. Sections command does the keyword sections, followed by series of symbol assignments and output section descriptions enclosed in curly braces. So this is the linker script. Actually looks simple, but you can go wrong in, because it's the VMA and LMA is pretty subtle, so you can go wrong in certain places. So you have to be aware of that. Now, coming to the next slide, you'll get a better idea of the memory layout. as to what is organized where. Let us rub this out and we'll proceed. Now, when this image is flashed onto the board, okay, so when you have compiled the program with these linker commands, and these are the options, and this is the memory layout. For our memory layout, whatever we have given, there could be various memory layouts, of course, as you know, and for our processor, this is the memory layout. So we have, this is how it is laid out. So this is increasing address. So from address, if we assume that the address is increasing from bottom to top, going from 00000 all the way to 4M, that is a memory address space that this Cortex M4 processor can address. Not everything is used though, but then, so underscore text, this value starts from 8 with 6 zeros. Okay, so it starts from 8 with 6 zeros, as we know, and the ISR vector is here. That's it, it's placed here. Then the dot text section, which is a combination of the text sections of all the files, input files. Then the RO data is a combination of all the initialized constant variables from all the files, okay, which is here. And then after the eText section, you have the data section. Okay, so the data is, this is the data, that is the LMA data. Okay, that is a logical memory address data that is in the flash that you need to copy over when the machine starts up. So that is the data here. That is, this section at its LMA is here. And then there is a BSS which comes after this. Okay, that is on the flash, the LMA of the BSS, but since the linker is very clever, it knows that the BSS section is like uninitialized and zero initialized data, so it doesn't copy anything here. The flash is not used up, but there's a non-existent .bss section. You can just imagine that there's a BSS section here, but it doesn't occupy any space physically. So this is the layout of the flash memory when the processor is powered down, that is just before power up. Now let's assume that we have now powered on the processor. We've connected the processor to power. Then a few things happen. This eText section, whatever data you have, goes into the underscore data section. That is this address location, whatever we have here, underscore data. It goes and sits in the data section. That is, this is copied during power up. When the power goes off, since this is a RAM area, this whole process needs to be repeated. And then this BSS section, whatever was the VMA of the BSS section, the size of the BSS section is of course EBSS minus BSS. So this is the size of the BSS section. So it is, so from this area, so you can see, I have put the name BSS Lite because there are a few things that go in here. First is the uninitialized and the zero initialized data and the stack. So what we do is we just zero initialize the whole region. So we take so EBSS minus eData is the size of this area. So we subtract it during the, when we see the startup script, we'll see how we do the subtraction and we fill this space up. So just after the initialization, this is the memory layout. This dot data area is no more used, at least during the runtime of the controller. This memory stays. Your code and everything runs here. It accesses data from here. So it accesses data, that is read-write data from here, and it does all the memory addressing, but it does not use this part. This BSS, non-existent BSS, is actually copied over to the, it's not copied because it's all zero. We just zero out take this entire area and set the value to 0 for all the memory that comes here between eData and EBSS. Whatever are these memory locations, the value can vary depending on the size of your stack memory, whatever you have assigned, and other things. Of course, this area can vary. You can have more or less initialized data depending on your application. So this is what happens. This is a manual step. We have to, manual in the sense we have to write code to relocate the data section to here and zero out this area. Okay. So this is the memory layout after power up. So before power up, this is what stays. This doesn't go. Immediately after power up, this is what happens during the initialized stage when the reset handler. So this is all in the reset handler. The reset handler is going to do the data copying and everything. There is the linker script symbol that we saw, and we even spoke of it. That is, these symbols are little weird. That is, if you declare a pointer in C, you have to say, for example, unsigned int star the variable name, and then you have to assign it to some address. Okay, but in the case of linker, you will see that there is nothing of that sort happens. We just declare the variable directly. That is, we just do underscore, say data equal to dot. Okay, this whatever we declare here underscore is not a variable. It is actually a pointer. So when we declare that in C, actually in our code, we have to use this kind of syntax. So let's see what actually this means. Now this is a variable where you will have the address of the variable. Of course, say when we declare a pointer in C, suppose we do int star x equal to some address location, something we ampersand some address of some variable. Okay, this star x or this variable, though it holds the address of this variable, this particular variable that it is holding the address of has a value, right? So say I have a variable called y, and y has a value of 30, and x is a pointer to this variable. So if it's a pointer to this variable, it will have the memory location of y, which is holding a value of 30. Here, in the case of the linker, it is something like a pointer variable, but it does not point to any location which holds a value. It just points to a location. That's all. Okay, so hope I've been able to explain this. So that is the reason why when you are dereferencing this variable in C, you just cannot do this. That is, you cannot do int foo equal to underscore EBSS. This is incorrect syntax. This is the correct syntax. In star foo, you have to give it, when you are dereferencing this variable, you have to give it the full pointer treatment here. So this is how you dereference the particular variable. And see, in a standard variable, if you see the symbol table, it will have a address and it will have a space reserved for that address. Okay, so int foo equal to test1, int star foo equal to ampersand test1, and so on and so forth. Now int foo equal to EBSS is not the right way to do it in the case of a standard variable. You can do it this way. Linker, this is absolutely not allowed because it never stores a value. So this is only allowed, this is not allowed. Okay. So no memory allocated, and it can be only accessed by its address. So this can only be accessed by its address. It cannot be accessed by any other means. So let us try to have a look at the startup file. Just briefly look at the startup file, and we'll see what we are talking about. Right? So this variable, if you try to access this variable, so when you go to the startup file, you are using, say, this value. when you come to the reset handler, it's a reset ISR. Okay, look at this. You have declared it as a pointer, and then you are grabbing the value with an ampersand. Okay, so this is what I meant to say. There is no other way of grabbing this value apart from putting an ampersand before this. So that is something that you have to keep in mind. So the linker uses two types of addresses for loadable and allocatable output sections. We saw that. Now the first is the VMA, or the virtual memory address, and this is the address the section will have when the output file is run. That is, the code will point to virtual memory addresses. Now the second is LMA, or the load memory address. This is the address at which the section will be loaded. So like the next point, there are certain cases where the VMA and LMA will not be the same. Now the symbol greater than is used to denote VMA, and the symbol at greater than in most cases is used to denote LMA. We saw in the previous case that the at was written at the beginning of the section. Okay. Now if neither at nor at greater than is specified for an allocatable section, the linker will set the LMA such that the difference between the VMA and LMA for the section is the same as the preceding output section in the same region. And we saw that when we were discussing the linker control script. We saw that here we do not talk about the LMA specifically. It just takes the difference of the VMA and LMA for the previous section, and it allocates the memory accordingly. Here, to begin with, the VMA and the LMA, it begins with the VMA equal to the LMA. So here also we do not do an at, but it assumes that the VMA and LMA is different. Sorry, it assumes that the VMA and LMA is the same. Here, since the VMA and the LMA diverge, here the difference between the VMA and LMA is maintained, and the assignment for the next section happens accordingly, provided we don't put another at the BSS section and wish to move the BSS into some other memory location. Now again, so this is a summary of what we spoke of. So the greater than flash here instructs the linker to set the VMA of the address to the flash. Okay, so here this greater than is setting the VMA. So the VMA is going into the dot text section through this counter. Okay, the dot here beginning with the flash VMA. Here the VMA is considered equal to LMA since no preceding output section exists. So here when it starts, we have VMA equal to LMA. Okay. Now here sets the LMA in the linker to fall just after the previous dot text section. So the LMA here, since we do an at here, the at section, the LMA forces the linker to put this data section just after the previous section. Okay. Now, so if the at was, say, not declared here, and we had just put the VMA to SRAM, okay, what would happen? So in this case, the LMA will become equal to the VMA, because if you do greater than SRAM and you don't put an at, what happens is both the LMA, so LMA and the VMA equals 2 with 7 zeros here. Okay, so you are actually not storing the data anywhere. That is, you are not storing the initialized data anywhere here. So you will have to use the at this point. So here it's just one stream of LMA and VMA is following one stream, and then here it bifurcates into LMA and VMA. LMA becomes different, VMA becomes different. All right. So, and that is necessary because you need to store the initialized data. And then again, the linker assigns the LMA here and in the flash region itself. So LMA is in flash region because it is following from here, and the VMA is again following, but the VMA is following after this SRAM location. Here again, here also it is continuing. The LMA and the VMA difference is continuing. LMA and VMA difference continues because here we are putting it in the SRAM only. If we had put this in some other region of SRAM, then again things would be different. Okay, so there are various permutations and combinations that you can have in this case. In our case, this is how it goes. So the linker assigns LMA here, and that happens to be in the flash region itself. But it also knows that the section to be zeroed out or it's allocatable. Hence, the output binary does not contain the section physically. So we saw that the BSS section is like an imaginary section. It does not contain this section physically. Let us drop it off. Now, how does the linker know that this section, this BSS section does not have any data? That is, it does not have any. It has uninitialized and zero data. It is because there is the type is no bits here. So linker knows that this one is this section is not to be written in the flash, but it will just have a virtual presence. And these sections are ignored by the linker script. It's not a part of executable binary. Okay? And we have to manually zero it out as we saw. Now this is how the VMA and LMA is assigned. So if we see the sections through the obj dump command for the output file, this is the output file, we see that the .text sections LMA and the VMA is the same. So this will help you to understand it more clearly. So .text section VMA is the same as the LMA. These are equal. The moment it goes into the data section, since we wanted it to be in the SRAM, it is the VMA has changed to this address. If you can see this 2 with 7 zeros. LMA is, we have assigned the LMA to be in 800054C. That is the just after this section ends, it writes the data section here. BSS section again, if you can see, it has a VMA of 2000008. Okay, and it has an LMA. Okay, if you can see, it has an LMA, but nothing is written in this region, and all these alignments are 4-byte alignments. So that is within these sections, and we saw that in the output map file that these are all within the section. If there is a misalignment, it byte aligns, but once it goes after when the section completes, it does not bother about the alignment, and the data section starts from wherever it has to start from. Okay. So, and of course the initialized data is just after this text section. So 54C, whatever you see within that, you have some initialized variable also. So this actually shows you how the VMA and LMA, it is the same, and when it bifurcates here, and it goes like this after that, until and unless of course you again write some linker commands to change this. So LMA and the VMA are separate. So this is an interesting concept. I hope I've been able to explain it properly to you. In case you have any questions, you can always ask me. Now, this is just a revisit of the LMA and the VMA that we saw. So it's nothing. We just before the power up, we have these values, and all these values are LMA values. Okay, all these values are the LMA values. After power up, when the new values are actually written, okay, so pardon me, this value is LMA and VMA. That is, whatever you had in the text section is LMA and VMA. Okay. So this was LMA equal to VMA. So when you saw that, this was LMA equal to VMA. So this does not get relocated. It stays here. The bifurcation comes from this here. So since the LMA and the VMA is not equal at this point, all of this needs to be relocated to this section. Okay. Because the LMA and the VMA changes here. So all of this gets written here. So I think this should clear your concept, and please have a look, keep looking at the linker document, that is the GNU linker document, and there are so many more concepts that you need to be aware of. We will look at one such concept directly from the linker document. So this is going to give you an idea of, this will help you to navigate the linker document better. And this is another interesting concept. Okay, so there is something called as, so we look at section 3.4.4. So this is alias. So assigning alias names to memory regions. Now, the idea behind this is you could be using, if you want to reuse the linker script on different processors with different memory layouts. How would you accomplish that? So say you, let us go to the document first. Let us go to section 3.4.4 of the document, and then we'll get a better idea of what I'm talking about. Yeah. So let's go to 3.4.4. So this is the alias names to, assigning alias names to memory regions. Okay. Now, let's say that we have, the goal is to provide a linker command file that contains a system independent part defining the output sections of a system dependent part of memory mapping. For example, we have three variants of processors. For example, one variant is variant A, where text, RO data, and BSS, everything goes into the RAM. Okay. Another variant is text, RO data goes into RAM, data goes into RAM and ROM, and BSS goes into RAM. And here we have text into ROM, that is the flash in our case. RO data goes into another flash area, ROM2, which we spoke of previously. It can be in another flash area. Data goes into RAM and ROM2. So data sits into ROM2, and it also sits in the RAM, and the BSS goes into the RAM as usual. Okay. Now notation RAM ROM or RAM ROM2 means that this section is loaded into region ROM or ROM2 respectively. Okay. It is loaded there. Please note that the load address of .data section starts in all three variants in the end of RO data section. Okay. So let us have a look at the script. So the script is, we'll be interested in this part, and it says it includes a system dependent link commands.memory file that describes the memory layout. So this memory layout, whatever we have, is described in a separate place. We could have it described in the same file as we saw here, but in this case this is described in a separate file. So here we have in the .text section, again, some files are going into the .text section, and this is region text. Okay, so it goes into region text, and then RO data section, it goes into region RO data. Now, we had a discussion a little while ago where we said that the RO data can be placed in some other region, and this is what is going on here. And then .data section, it changes to a different location. So this is the LMA is getting changed here at the .data section to RO data end. Okay. And then, but the VMA is in region data, data size, and then you see something called as a data size variable, okay, which is the size of RO data, and so on and so forth. And then the data load start is load address of RO data, and so on. And then you have the BSS. The main thing that we need to be aware of is, so this is one script that we see here. Now, when we come here, we see 3 different link commands memory files, okay, to define the memory regions. Okay, 3 variants. One variant says this is the memory, okay, that is everything is in the RAM. That's the first variant, and there is region alias, okay, commands which actually maps these regions into different places. For example, region text is in RAM, region RO data is in RAM, region data is in RAM, region BSS is in RAM. Okay, so this is region alias. So with the alias, for example, you see here it changes in the second variant, it changes to the second, whatever we have in the second column, ROM, RAM, and in the third one, so here the memory layout is this, and then the alias is this. In the third, the memory layout is this, and the alias is this. So we have different memory organizations, 3 separate files. And so the main concept here is, if we have 3 separate files, each containing one variant of the memory layout here, we have the name of the regions the same, but they are mapped to different memory regions. For example, region text, region RO data, and region BSS. So coming back to the script, we have region text, region RO data, and region BSS. So depending on what we include here, we may not include the file here. We could put this entire section into that particular file also. That also is permissible. For example, having this put on the top, but then this one makes it more flexible. That is, we can create a separate memory layout file, and we can include the file, and during link time the linker picks up that particular. So this could be link commands variant 1 dot memory file, link commands variant 2 dot memory file, link commands variant 3 dot memory file, and so on. Okay, so that is one concept that is pretty useful, and when you are having to deal with multiple memory maps, you could use this technique.